Okay, so now that we've looked at the slope, let's take a look at the other thing that we can find from our velocity versus time graph. So we took a look, we were on velocity versus time, we looked at the slope, and we found our acceleration. From velocity versus time, we can also look at the area under the curve and find our x, our displacement. Okay, so let's start off at the very beginning. I've got a situation where if I want to look from time equals 0 to time equals 1, I've got this shape right here. And the area under the curve looks like this. Well, what shape is that? That's a triangle. So the area of a triangle equals 1/2 base times height. Okay, well my base is 1 second. My height is from 0 to 3 meters per second. So I would plug this in, I would get equals 1/2 base is 1 second. Height is 3 meters per second. And so I evaluate this, I end up with 3/2 or 1.5 meter per second times second. The seconds cancel out, I'm left with meters. We can see that my units will actually agree. Just as we did earlier, we had meters per second divided by second, and we got units of acceleration, meters per second squared. If you forget what you're looking for on the graph, let the units tell you. If you've got seconds along here and meters per second here, if you find an area, meters per second times second will give you meters, so you're finding a displacement. Or if you find a slope, that's meters per second divided by second, meters per second squared, you're finding an acceleration. Okay, so we found an area here. That's our displacement. And in fact, let's see. If we want to verify that, we start off at 0, we end at 3 meters per second, and our total time is 1 second. Let's get one more thing, something that we're used to. Let's double check that. We've got 1D kinematics, so initial velocity was equal to 0 meters per second. That's from our graph. Down here, at time equals 0, we're at 0 meters per second. Our final velocity is 3 meters per second. And the time is 1 second. So our total time equals 1 second. Okay? If I want to find delta x, I would use my equations. I believe the equation we want is delta x equals 1/2 v1 plus v naught times t. Double check. Take a look at the kinematic equations I gave you. That should be it. If I plug these in, I have delta x equals 1/2 times v final, which is 3 meters per second, plus v initial, which is 0 meters per second, times time, which is 1 second. I end up with delta x equals 3/2. These are meters per second, canceling out with the seconds, meters. So our kinematic equations, which we're used to using, tell us the same thing. We find that with our approach to seeing it on a graph, we can actually find the area under the curve. The velocity versus time graph gives me my displacement. All right, let's check one of the other displacements on here. All right. Let's take a look at from t equals 4 to t equals 6. So I'm looking at this area. Well, it's a little more complicated. I've got this part here, which is a triangle, and then I've got this part here, which is a rectangle. So if I want to find my total displacement in that period, okay, I've got, this is 1 second, and this is 1 second. My heights involved here are 0 to 2 meters per second. So I'm going to split this up. I've got area 1 and area 2. Okay? And my total area, A, will be equal to A1 plus A2. Well, if I look at area 1, what shape am I dealing with? I'm dealing with a triangle, so that's going to be, for A1, we've got 1/2 base times height. My base is 1 second, so I've got 1/2, 1 second, times my height, which is from 0 to 2 meters per second. My height is 2 meters per second. I multiply that out, and I end up with, the per second cancels out with the second, that 2 cancels out with that, and I end up with 1 meter. My displacement from the triangle here is 1 meter. All right. My second area, this rectangle, it is base times height, is the area of a rectangle. And my base is 1 second, times my height, which is still 2 meters per second. Seconds cancel out. Well, second and then divided by second. And so I end up with 2 meters. So my total area equals 2 meters plus 1 meter equals 3 meters. So I found my total displacement for this particle from time equals 4 to time equals 6, just by splitting it up, looking at the areas, and adding them together. Now, unfortunately, I can't go in and verify this for you, at least as easily, with the kinematic equations here, because my kinematic equations, they only hold when acceleration is constant. Well, I've got a slope here that isn't 0, and then a slope here that is 0. So during this period, I do not have constant acceleration. So what I'd have to do is break it up, and I can solve for the displacement here and the displacements here. I'll leave that as an exercise for you, and then that way you can check it out. You can apply, because in this region, we have a constant slope, so a constant acceleration. You can find the displacement in our triangle area, and you can do the same over here with the rectangle with a constant acceleration. And in fact, because that's a flat line, we know that our acceleration is equal to 0, because it's the slope. Okay? So that is applying what we know here, our graphical kinematics, on a kinematic graph.